And today, we are honored to have Professor Neil McIntyre from the University of Queensland, Australia, who will do a presentation related to a very important subject for our Chilean mining industry, which deals with the flooding of abandoned tailings dams and how to assess these risks in our country. Before we go into the more details about the presentation, I would like to give some background information of Professor McIntyre. Professor McIntyre has a Bachelor in Engineering and a Master of Science degrees in Civil and Environmental Engineering from the Edinburgh University and from the Imperial College in London. And he also holds a PhD in water quality modeling and uncertainty analysis from the Imperial College. Professor McIntyre worked for 6 years as a water engineer in the Scottish water industry. And after that, he moves to Australia to the University of Queensland, where he teaches hydrology and leads research on the planning and management of land and water resources in mining regions. And all this research includes water balances of operational, closed, and abandoned mines, the hydrology of these mine wastes, and covers and water security assessment and fundamental research into hydrological processes and modeling approaches. So besides, I have to say that Professor McIntyre is a very respected scientist in the Chilean mining community, and I would say that in the world community, mining community. And he's also an active collaborator with the work we do here in the Water Research Center for Agriculture and Mining in CRHIAM of the University of Concepcion. Before we start with the presentation, with Neil's presentation, I have to say that during this presentation, people can leave questions and comments through the Facebook Live transmission chat. And all these questions and comments will be taken at the end of the presentation and will be asked to Professor McIntyre. And so now, please, we all welcome Professor McIntyre with his presentation, which is entitled Flooding of Abandoned Tailings Dams, How to Assess the Risks in Chile. Please, Neil, feel free to start whenever you're ready to.
Well, thank you, Leopoldo, for that very generous introduction. And it really is a pleasure to be able to contribute to the series of communication activities that you're doing at the CRHIAM Center, which are extremely impressive and important. Before I start, just let me apologize in advance if there's any background noise here. My 5-year-old daughter is just getting ready for school and I'm at home. So apologies for that if that happens. Shouldn't be too bad. So as Leopoldo says, my background is really hydrology, and much of that is flood hydrology. But for the last 7 years, I've been really focusing on sustainability of water resources in mining regions. And so it's been great for me to be able to combine these two passions of mine, flooding and mining sustainability, to look at this really important topic. Important in Chile, also important in Australia because of the large number of abandoned mines that we have here, which are potentially exposed to flooding. The work I'm going to present has been a team effort between these collaborators that I list here, but the large majority of the work's been done by Gabriel Perez Murillo, who's the PhD student working on this, and he's funded by a University of Queensland scholarship with support from SMI ICE Chile. I also need to acknowledge CSIRO, who have been an important partner in providing one of the models that we're using, and Sarnagio Min, who aren't a partner in the project, but have been extremely helpful to Gabrielle in providing information required. So I've got about 30 slides to go through, separated into these 3 parts, and all going well, I'll be done within 30 minutes, leaving plenty of time for questions. So first of all, I'm just going to give a bit of an introduction to tailing storage facilities and abandoned tailings dumps and their risk assessment, just for those who are listening who don't have a specialist background in that area. So tailings are the byproduct of the production of metals and minerals from ore. And large volumes of this waste are produced. They tend to be high in water content and need to be safely stored in tailing storage facilities. There's a large number of different types of facilities and different environments in which they're situated, which is important when we're considering environmental risks from them. So many, in particular modern tailing storage facilities, are in constructed dams which are built to very high engineering standards and are monitored very closely for their safety and performance. And then there's tailings embankments, which are similar but are constructed from the waste tailings themselves. And even though under good practice, they will be highly engineered and effective, the history is quite variable in terms of their performance and the quality of the construction. And then there's abandoned tailing dumps, which really either have very rudimentary embankments or don't have any embankments at all. And these tend to be from small scale mining, and in some countries illegal mining, where the tailings have essentially been just dumped. And often these dumps are in not necessarily in safe locations, but are in convenient locations for the mining, which is often on river floodplains, which is why they're one of the reasons why they're a particular interest for this topic. We also need to distinguish between wet climates and dry climates. So in wet climates, there's a persistent excess of water coming into the tailings storage facility, just because of rainfall and the run-on of that rainfall into the tailings storage facility. And this means that unless it's very carefully managed, the pore pressures can build up and there can be overtopping of the dams. So the water balance of the tailings is very important in the design and the operation of the tailings facility. And then there's very dry climates, which we experience over much of Australia and over much of Chile, where because of the high evaporation rates, the surface of the tailings becomes essentially desiccated and dust becomes the major issue. However, as we'll see in my presentation, even though areas may be arid and dry and primarily suffer from dust issues, that doesn't mean to say they're free of flooding risks as well. Now, all these different types of tailings facilities are relevant to my presentation, but potentially most relevant are the abandoned and inactive tailings storage facilities and dumps, and there's a few reasons for that. First of all, on the right-hand side of this slide, you see some results from the Trunque program, which is run by Fundación Chile, which is a really excellent program in Chile. And one of the outcomes from their review work was that although there's been a lot of progress in the risk assessment and management standards for large-scale and medium tailings storage facilities, it's the small-scale abandoned tailings deposits where there really hasn't been sufficient progress in understanding the risks and producing guidance to manage these risks. Now, the very nature of abandoned and inactive tailings deposits mean that there isn't a private company who has active responsibility for managing the risks. And therefore often falls to the municipalities and other relevant government authorities to do their best to manage these risks. And that's difficult just because of the sheer number of these facilities and because of the limitations on funding available to manage the risks. Now this is important in Chile. As you see from the top photograph there, A lot of these dumps are situated on the floodplain next to rivers, and therefore when we do get extreme floods coming through, there can be significant erosion and release of contaminants inside the tailings. And then these are transported downstream and can be either affect water that's used for irrigation or potable water supplies, or can remain in the soil and the sediments, or can infiltrate down into groundwater resources. And many towns in Chile, because of the history of mining, have these dumps either within the town or on the periphery of the town. So in cases very, very close to communities. Just a few statistics. CRHIAM has a very helpful database of tailings storage facilities over the whole of Chile. And it shows that 86% of these are abandoned or inactive. So that really exhibits the scale of this problem with these small-scale abandoned and inactive dumps. You can see from the map there, these red dots are the locations of tailings storage facilities in Chile, and you can see that there's a large number and also spread over large parts of Chile, primarily in the central to north of Chile. Now this large number and the diversity of locations means that it's very challenging to actually focus on a particular region and decide, okay, this is the region where the greatest risks lie, and this is the region where we have to pay most attention to understanding these risks and managing them. What I'm going to talk about in my presentation is the difficulty of doing a comprehensive risk assessment when you have so many facilities in such diverse areas and environments, and the need for simpler risk assessment tools that allow a pre-selection in order to help prioritize. Now, risk analysis of contaminated land in general, and including tailings storage facilities, is a very well-developed topic, and a typically applied framework is called the source pathway receptor consequences framework, where you would do a detailed evaluation of the sources, in our case, the tailings, including the geochemistry and the physical properties, and looking at what contaminants exist in them. And to some extent, this has been done in Chile by CRHIAM. And then you would undergo a modeling of the pathways, so the potential release, and this could be under floods or it could be under seismic or other natural hazards, and then the transformation and transport of contaminants as they move through the catchment, and then look at what's actually important downstream that this contamination may influence, and then look at the actual consequences, either economic, environmental, cultural consequences, and put that together into a risk matrix, and then identify which the priority sources are. And indeed, there's well-developed guidance on applying this framework, for example, by the European Union, specifically for mine tailings. That's the PRAMS project. However, that's expensive. To do it for a very large number of sites is probably impossible due to the resource requirements. And therefore, I go back again to the need for pre-selection, less expensive pre-selection frameworks that help the prioritization. So just in summary of that introduction, we are lacking progress in understanding and managing risks from small-scale and abandoned sites. This is especially important in Chile. Flood events are expected to be rare, but increasing under climate change with the potential to expose tailings to create high risk. And due to the large number of sites, pre-selection methods are needed rather than full risk assessment procedures. Okay, so the research we're doing, so the basic question, what is a suitable flood risk model for pre-selection of tailings storage facilities prior to full risk analysis? And the approach we're taking, well, we spent some time just looking what would be suitable case study areas in Chile to really test these models, to look at what potential suitable flood simulation models exist, start from complex to simple, compare their accuracy and applicability. And then in brackets here, because we haven't done this yet, but this is the intention, to encompass these models within, or the preferred models within a more complete risk assessment framework. Now, just a bit about scope. Now, there are lots of different types of flooding, which somewhat complicates the question, so that there can be flooding due to run-on of rainfall from the hill slopes directly onto the tailings, which can result in dangerous pore pressures building up and can result in overtopping of the embankments or dams. We're not looking at that. What we're looking at here is inundation of the floodplain, whereby the water levels in the rivers burst their banks and they then have the potential to scour and erode any tailings dumps or any embankments that are situated on the floodplain. So we're really looking at models that predict this increase in river levels during these extreme floods. So case studies. So as I said, we spent quite a bit of time looking at case studies, and I'm just going to flick through a few of them because it had some very interesting, insightful results into the nature of the problem. So there's many basins in the central to north of Chile where you start looking at the locations of these small-scale tailings dumps, and you find they really are situated on the floodplain, in some cases actually within or very close to the river channels. And not only that, but are situated nearby or upstream of communities or important ecological or economic assets such as farmlands. So this is the Elche River Basin, in particular the Quebrada Marquesa area, which we considered. We also considered the Limarí River Basin and in particular the Punitaqui area, again with a very interesting cluster of storage facilities. Thirdly, the Los Chorros River Basin, again, you can see that cluster there just at the end of the steep part of the river where it's coming out into the productive lands. But in the end, we settled on the Copiapó River Basin, and in particular, the area around Copiapó City that's shown in the right-hand side of this figure. And the reason for this is that there is a large number of tailings facilities here. In fact, there's a total of 61 inactive and abandoned facilities highlighted here. Many of these on the periphery of Copiapó City itself. Copiapó City experienced a very extreme flood in March 2015, which I'll show some information about that in the next slides, but basically that flood was relatively well observed. Even though there's no flow gauges in Copiapó City, the peak flood levels were relatively well observed and therefore give us quite a good basis for testing flood models. Thirdly, our partners CSIRO had already developed a state-of-the-art flood inundation model for Copiapó City. So we really had a good opportunity here to test that state-of-the-art model against more simple flood modeling tools, just to look at the exposure of this large number of tailings facilities to floods. Now, I mentioned the large event in March 2015. This is a heat map which tries to illustrate the significance of that event relative to the history of flooding in this area. And the heat map shows maximum daily precipitation. So the red values are the dry times. The yellow values are just the normal precipitation rates. And then these green and blue values are the extreme events that have occurred historically. So you see that March 2015 event highlighted here. It was about 70 millimeters of rainfall, fell over a few days. Now that's not much rainfall in global terms. In where I live in Brisbane, that's very, very little rainfall actually. Because of the nature of the Copiapó region, it's very steep. The land is relatively impermeable. It means that rainfall, almost all of that rainfall is translated into flood water. And that's what makes this a damaging event, a very fast, high energy flood. You also see here that this flood event wasn't remarkable, according to the historical statistics. There have been similar or greater events in the relatively near past. So you see that the time series here is a time series of flow measured at a gauge upstream of Copiapó. And again, you see the remarkable feature of this flood event is the very fast rise on the 25th and 26th of March. So a very rapid increase from normal flows up to that very high flood peak. And that very high flood peak resulted in widespread damage, as you see from some of the photographs here. As I said, this was relatively well observed, which is good for us, including observations of which tailings facilities were exposed to this flood. Now, just as a quick aside, on the bottom left of this slide is some of the rainfall data for this particular event over the Copiapó Basin, which has been reconstructed by the CR2 project. Now, this type of climate data is extremely important for understanding flood risks. And we're now at a stage where, with projects like the CR2 project, we are in a much better position to understand historical and future flood risks. A bit about the CIRO-SWIFT model. So this, as I said, this is a state-of-the-art flood inundation model based on the shallow water wave equations. And I'm not going to go into the equations at all, just we can just accept that it's a commonly used type of model where we need to understand in detail flood risks. And you see on the map here, the observed inundation extent during that extreme flood, and the observation points where we actually have observation of the flood levels with which to calibrate and assess our models. Now, SWIFT is a state-of-the-art model, but it's expensive. It needs considerable level of expertise and time, and I mean several months, in order to apply it properly. So while we expect it to give accurate results, it's expensive to apply, and it's questionable whether it's applicable over a very large number of sites to assess risks. Also, to get the best out of this type of model, you need a high-resolution digital elevation model, which isn't available nationally, and would require to be purchased from a commercial supplier. The much simpler model we compared was called pueden. This is a much more empirical model which uses geomorphologic concepts. So it essentially fits empirical relationships between the catchment area and the expected flood height based on different classifications of geomorphology. So this is a well-established type of model as well, which is used where we need approximate indications of what potential floodplains are going to be. So this potentially can be applied much more inexpensively and rapidly over a very large number of sites. The question is it accurate enough relative to the more expensive complex methods? Does it give us useful results in terms of exposure of tailings to floods? This is just some of the calibration work on this model showing the difference between the lines and the dots there are basically the difference between what the model says and what is actually observed. And as we expect with this type of model, you get some very large deviations. So we can expect some very large errors from applying this type of model. So we undertook a process of comparing these two models. And this map shown here is a map of the Copiapó city area, the case study area. And in green there, it shows where the two models agree with each other. And in red, it shows where they disagree, where SWIFT predicts an area to be flooded and pueden predicts that it's not flooded. So the key point here is there's a very large number of pixels there, which the more complex models predict are going to be flooded, in particular in that urban area. And it's along the channels, the main channels, that the two methods agree with each other. So you see up at the top, the dry areas are easy because they're not areas that any model would predict to be flooded. And so there's high agreement about these dry areas, but there is a significant amount of areas, almost 5%, which SWIFT predicts to be flooded, which the other model fails to predict. So we then went on to say, well, okay, we understand from this that SWIFT gives better predictions. What does that mean in terms of how well it captures which tailings facilities are exposed to floods? And so of the, I think it was 61 abandoned and small and inactive facilities in this area, the SWIFT model predicts that 33 are going to be exposed to this March 2015 flood. And while the GF plane predicts that only 8 were exposed. And the SWIFT predicts a much higher maximum flow depth of exposed. So it's really significant differences in the number of tailings storage facilities at risk from this flood between the two methods. Now, if we talk about prioritization, we're not necessarily interested in all the sites that the models predict to be exposed to the flood. We're really interested in the priority ones. You know, which are the ones do we expect to be most exposed to the deepest and fastest floodwaters, and therefore the most prone to erosion. Now, if you look at the top 3 predicted by GF plane on the right-hand side there, that's codes 50, 35, and 16. We find that 2 of these are in the top 4 predicted by SWIFT, and the other one is way down the rankings for SWIFT. So in other words, if we relied on the GF plane model for this case study, and we took the top 3, its top 3 rankings, we would have a 50% success rate relative to what SWIFT would predict. So the outcome is that GF plane is much more applicable in practical terms to very broad scale risk assessment involving hundreds of sites. But if you're going to do that, you have to accept that it may have around about a 50% success and 50% miss rate in terms of identifying these really at-risk sites. But the story doesn't end there, because what we had assumed when running the SWIFT model was that to get the best use of that model, we needed to apply a 5-meter resolution DEM. And this is just a simple illustration of the different levels of detail you get when applying different resolutions of DEM. That's a digital elevation model. So you see up there, the 1-meter resolution gives a very good definition of the river channel there, and very nice definition of the tailings storage facilities that are sitting next to the river channel. As you move from 5 to 12.5 to 30 meters, these definitions become less and less. And at 30 meters there, you see that really the river channel isn't delineated at all. And therefore you would expect that low resolution to be pretty useless for this purpose. But what we found was actually, while it would normally be recommended to apply the 5-meter resolution for SWIFT, we found that actually the 12.5-meter resolution worked quite well with SWIFT. So this is significant because it significantly reduces the costs of obtaining the necessary data and the time required to run the model if you're to use that lower resolution DEM. So there is still a question there about if we accept lower resolution DEMs, how applicable then would SWIFT be? To conclude the presentation, I'm just going to talk a bit about ways forward. Ways forward both in terms of what we're planning to do in this project, but also what might be done in other projects. So we've only looked at a small component of the overall problem. We've only looked at exposure of these tailings facilities to floods. That needs to be put within a broader risk assessment procedure where we consider the properties of the source, that's the geochemical and the physical properties of the tailings themselves. And if they are exposed to floods, what does that mean in terms of the transport of contaminants down the catchment? And and who and what is exposed to these contaminants. Now, what Gabriel has started doing in his PhD is looking at the geochemistry data provided by Sarnacchio Min, and indeed this data is starting to show that there are significant contaminants in some of these tailings facilities in terms of being above standard safe levels. Now, what we need to go on to do is actually look at specifically what are the key contaminants in terms of downstream risks, and also which of these tailing facilities which are at risk from flooding hold these contaminants. So that's ongoing work. Our ambition is once we've done this for Copiapó, is to then say, well, you know, how can we convert this into a tool that can be rapidly applied over for many, potentially hundreds of sites in these different case study regions in Chile. Now that's a significant undertaking, which will probably need another subsequent project to get to, but that would be very nice because it would allow us to then start producing meaningful maps of priority at-risk sites over the whole of Chile. Now, thirdly, there's the question of climate change, and this is something that's been looked at considerably in the Climate Risk Atlas of Chile project, which is recently finished. So we did the tailings work under that project, but that was limited only to looking at climate indices. In other words, there wasn't any flood modeling done at all. It was only looking at how extreme precipitation is expected to change under future, and how that relates to locations of tailings facilities in Chile. So we were able to produce some heat maps saying, okay, this is where the most extreme changes in extreme precipitation are expected, and this is where that is superimposed upon clusters of tailings facilities. So there is a question of whether this climate atlas work can be taken forward to include simple flood inundation models as well. So in conclusion, we think that geomorphologic or other simplified, for example, low resolution SWIFT models could be applied in key regions with high concentrations of tailing storage facilities, combined with other aspects of the risk assessment process to produce at-risk maps over the whole of Chile. And then the priority sites, perhaps the top 10% or 5% of sites from that would then need to go forward to a more comprehensive source pathway receptor consequence modeling process. Now, the models are not infallible at all, and therefore there would need to be a good dose of expert opinion to qualify the results and to moderate the results and decide which of these model results we really believe and which we don't. And then subsequent to that, having identified the high-risk sites, then of course management plans should be developed, which would actually exclude floodwaters from these sites. Thank you, that's the end.
Thank you very much, Neil, for such an interesting presentation. It is amazing to see how many tailings dams we have in the north of Chile that we don't know. And each of them represents a risk, an important risk. So as you said, if we have rain there, even though that rain may be very, very small, you can generate a lot of problems. So this is actually a very, very important, I think,
yes,
subject for society, not
yes,
just for mining, but for society.
Yes, but we need to also recall that many of these tailings don't pose a great risk because many of these tailings, they're not high in contaminants. Okay, so then hence the importance of understanding the geochemistry as well, because it could be we identify the top 3 priority sites in terms of exposure to floods, but we could find that none of these tailings are high in important contaminants. Mm-hmm. So I would say it's a very important problem. I wouldn't say that there's hundreds of high-risk sites out there. I would say there's probably a few, and we need to identify which ones they are.
Yeah, that's what I meant. I mean, we don't know. We don't know how many they are. So that's actually something important. And you know, well, Chile is a mining country, and I think it's gonna continue to be a mining country in the future. But for some reason, society sometimes doesn't like too much the mining, and there is something like a not so good image of mining, and in particular with the tailings dams, you know, even though they don't generate any problem, but the society has some kind of bad idea of these tailings dams. What do you think we could do to improve that, to improve that kind of image of the mining and of the tailings dams?
I think society is quite right to be concerned and be suspicious given occasional international catastrophes and research which shows that there's more pervasive risks as well as these catastrophes. I think I'd like to be quite positive about that. I mean, it's a question we could discuss all week, right? I mean, you could have a whole conference, and there has been whole conferences, whole conferences just discussing that question. But in the context of Chile, I'd like to be quite positive and say, actually, Chile is doing a lot of really good things. I mean, starting at the fundamental research level, the kind of research we are doing and the kind of research you're doing in CRHIAM is important. And Chile not only has that fundamental research, but it actually has a structure of research centers aimed at delivering that research into practice, right? So, I mean, Chile actually has some quite impressive things going on and impressive frameworks to take new research into practice. There's also the program Tronques project, which is really impressive in terms of promoting transparency, promoting information, promoting education. And I think that's what's really missing in many parts of the world and has been missing in the past in Chile.
How far do you think we are from having a good risk assessment method here in Chile? Are we far away from that, from having that kind of tool all along the country?
I don't think so. I mean, I think all the knowledge and tools are there needed to do it well. What it needs is funding, basically. It needs funding and it needs the right group of people to do it. I mean, it's by no means a trivial exercise. I mean, you can see from our work, we've, Gabrielle has spent 2.5 years now working on this and has only looked at one small part of the problem. So I think it really needs initiatives and potentially the centers that we're involved with are the places to take these initiatives. But, you know, it really needs a collaborative effort. I mean, the other thing that's done well in Chile, I think, is CRHIAM Min. I mean, I've done some really good work in developing a database of the tailings and doing some research into some of the properties of the tailings and actually publishing that and actually looking at, you know, what effects, what are the benefits of publishing all this. The danger is that, you know, that kind of effort won't be well enough resourced into the future. And I think that's another key thing that, you know, these great pieces of work that are being done in Chile, you know, this isn't a short-term problem, right?
Yeah.
I mean, this problem is going to be here in 10, 20 years' time.
Absolutely.
And these things need to be well resourced for many years into the future.
Yeah, you know, in the mineral processing chain, we always talk about integrating the knowledge from the mine to the process, you know, and people say that we should also integrate all the knowledge from the mine to the tailings and from the mine to the concentrate, or to even to the cathode.
Yeah.
So,
Absolutely.
as you said, this is a long-term project, and we should actually, you had in the University of Queensland the designer tailings project, right?
Yes.
That was the idea, right? To
exactly,
integrate from the mine to the tailings. So how do you build the tailings dams based on the minerals that you process, and based on the geochemistry and on the reagents that you use?
Yes.
I think that it should be taken that way, right?
Yeah, and I think there has been progress in that, in integrated models from the mine to the mill and to the properties of the tailings. I think probably we need to take that one step further to look at the actual behavior of the tailings in the facility, the storage facility, and what that means in terms of environmental and community risks. So I think there's been a lot of progress, and that's ongoing, but there still is a missing link there we need to address.
Now there are some plants, concentrators in Chile that are using seawater. Do you see any additional risk of using seawater related to the tailings dam building? I think all the geochemistry changes a lot in the tailings dam.
Yeah, well, I'm not a geochemist, and so I'm not qualified to answer that in terms of the geochemistry. I know that your groups are doing a lot of really good work in looking at the implications of using seawater for mineral processing and solid liquid separation. So that's excellent. In terms of water, I mean, the key thing in terms of risks associated with the water content of the tailings is just to ensure that a high proportion of the water is removed prior to the storage of the tailings. So, I mean, if the use of seawater actually increases the residual water after the separation process, then that is a risk, yes. So that's your job to make sure that doesn't happen.
Exactly. You know, I was talking to the colleagues some days ago and about all this idea of using desalination plants. You know, in the future, you know that our grades are decreasing in our country, so we need to use more water. So most of the people say that we'll get that water from the ocean, and for that we need to use desalination plants. So that means that we need to take water. We'll bring the water from the coast to the mountains.
Yeah.
So I was thinking that, what about climate change in those areas where we didn't have that water, and now we are going to have water coming from the ocean? Do you think that could change the climate in those mining operations around there? Because that water will evaporate, right?
Yeah, that's a very interesting question.
We don't know, I think.
We don't know, but I think if you look at the water balances, the atmospheric water balances, the volumes of water being pumped from the ocean are completely negligible. So I mean, it's an interesting question, but I think it's an academic question. I think the concerns about seawater are more the engineering concerns of the mining and mineral processing, and the environmental impacts of the desalination and the water transfer. Yeah.
Okay, let's go into some questions from the audience now. The first question says, what elements do you need to consider to building tailings dams in the long term? What do you need to consider to design these new tailings dams in the long term?
Yeah, that's a very good question. Well, clearly the standard of the structural standard. So the dams, tailings by nature, exert significant pressures, of course, on the embankments and dams, and so there needs to be good geotechnical and good structural design of the embankments and dams. But that's that's well known. I mean, the standards both for construction and for maintenance are there. It just needs commitment to follow high standards and not to cut corners with costs, basically, because I think that's where the major problems in the past have occurred due to the pressures to cut costs and lack of following the applicable guidance that's out there. In terms of water, of course, it's important that as far as possible, the catchment water is separated from the tailings facilities. So it's important to have channels that divert runoff from the catchment around the tailings facilities and safely discharge it downstream. So that has multiple benefits. The engineering of, there's a whole bunch of engineering considerations, like the use of suitable membranes to prevent seepage and drainage, so that any seepage can be intercepted and recirculated. But these are all very well known things. I think the challenge is more, what do we do about these facilities that historically have been built or dumped, whatever, where these contemporary standards haven't been applied or haven't even existed at the time.
Okay, the second question is, great work, congratulations. In terms of time, what was the difference between the two models that you presented? And what is the advantage with each kind of model?
Yeah.
What is the advantage of any of the models?
Okay, well, in our project, we benefited a lot from the fact that CSIRO partners had already constructed and set up this model for Copia Post. So the time requirements for us were more about changing the inputs to the model, looking at sensitivity analysis to resolution and things. But even then, it's been several months of work. So I expect even for an experienced inundation modeler, every case study is going to be a matter of months of work to appropriately set up the model. You need data on things. You need DEMs. You also need data on roughness and slopes and any structures on the river, et cetera, et cetera. So a large amount depends on what data is already to hand on these things and what you need to actually go out and collect. But I would say for the simpler method, it would be a matter of days to set up a model for a catchment once you knew what you were doing. And for the Swift model, it would be weeks to months to set it up if you had the data you needed.
But I guess
the advantage of the latter, one thing I didn't cover in the presentation, I mean, the Swift model is a hydrodynamic model. It gives you out all the relevant variables. It gives you the flood depth. It gives you the flow velocities in 2 dimensions. It gives you the flow energy, and it gives you the timing of flow as well. So it not only says, well, the maximum level is going to be this, it tells you the duration of the exposure. So it provides you everything you need. Whereas the GF plane is essentially gives you levels. And these levels, as we've seen, can be quite inaccurate. We only looked at I only showed you our work on levels, but other indices that are relevant to erosion are, of course, the velocity of the water and the energy of the water. The GF plane model won't give you these.
Well, sometimes you have very nice models, but you don't have all the data to run those models. That's the problem.
Yeah.
And I guess the CSIRO model needs more data, more information to work.
It does, but I mean, the main inputs to both methods are the input flood hydrographs, which comes from a hydrological analysis. So you need to do that for either method, and then the DEM. So these are the basic bits of information that you need for both. The additional information for the Swift model is, it works on the basis of energy, of momentum balance. And so if there's any barriers to the flow, such as bridges or culverts, you need information about them. You need information about flow resistance from roughness. So there is significant additional spatial information you need if you want to do it well.
Okay, question number 3. Hi, I would like to ask about how to integrate different levels of production, mining production, to minimize and optimize the tailings generation and to reduce water consumption. How can we integrate the different production levels in the mining operations to minimize? It's not an easy question. Actually,
that's a question you can answer better than me.
Maybe, I don't think so. But this is not an easy task, right? It is what it is.
I think all I can say is we're working on it. our colleagues are working on it, but I can't, you know, I don't have a mining engineering background, so I just can't answer that well.
Okay, question number 4. Thank you for your presentation. In your conclusion, you said that experts should be consulted to decide which model is good. But before that, you told that geomorphological method should be used just as a first approach. In which case, geomorphological methods could be considered the definitive, I guess.
Yeah. Okay. So let me clarify. The conclusion I made was that geomorphologic methods or other simplified methods should be used. As I showed, when I showed the sensitivity to the DEM, I left open the question that actually SWIFT might be more applicable if we were to revert to lower resolution DEMs. And so I've left open the question whether, you know, the simplified model could be achieved simply by lowering the resolution of the SWIFT modeling. I can't say for definite that would be better or worse than using the geomorphologic method. The expert opinion, I mean, models are just tools, right? We know from the outset that the model is going to be wrong in some respect, because models are just by their nature some kind of approximation of what's really happening. In my experience, so I've been, you know, essentially a modeler for 30 years or so, and I have the strong view that in many cases, a simple expert opinion gives you equal or better results than a model. And I'm saying that as a modeler. So the model is a tool to support our decisions. The decision has to be made on the basis of both the model and other sources of information, including basic expert opinion.
Yeah, I agree. Okay, question number 6. The DEM model of the Copiapó Basin, was it a private source, or you got it from CRHIAM?
No, we bought the DEMs, the high resolution DEMs, 1 meter, 5 meter. They were purchased. So, I mean, CSIRO purchased them themselves for doing their own modeling, but we also purchased them as well so that we could use them freely. And we purchased them for all the other case studies that we're targeting. You can get, the free DEMs are at 12.5 meter resolution, which is the one we used for the GF plane. So our initial view was that, well, that's another advantage of GF plane because we don't need the high resolution DEMs. We just use the freely available ones. But as I commented earlier, there is an open question of whether you could actually run SWIFT using these free DEMs as well, even though it's not recommended.
What was the methodology to determine the parameters of calibration of the 2D models? That's another question. How did you get those parameters?
Yeah, so that's a good question, which I can't answer very well because it wasn't me who did the detailed calibration. So much of the calibration work was done by CSIRO. So they've published.
Oh, okay.
They've published on this. So if you do a search for CSIRO, Chile, Copiapó, flood, SWIFT, then there'll be a document which describes how the calibration was done. And then I think Gabriel did some adjustments to the calibration as part of his work as well. Generally, it's the roughness parameter, because the roughness parameter is the big unknown in these models. And so generally, you adjust the roughness of the channel and the roughness of different land cover areas, such as urban areas or vegetated areas, in order to match the observed simulation. So I mean, it's an interesting question, and it's a big it is a big question in use of these models. I can't give a very satisfactory answer, but there are. It's a very well studied area how to calibrate these models. So there's a whole bunch of literature out there on how to do that in general and how it was done for this area.
Yeah, there's another question that I think it's also important in terms of the monitoring. Which variables do you think are important to monitor in the tailings dams, or such as precipitation, sediments, contaminants, and maybe strain or something like that from the geotechnical side? I know there are some sensors that measure strain or different changes in the geotechnical variables, but
yeah, well, certainly from a geotechnical point of view, the pore pressures, any changes in pore pressures behind the embankments, changes in the strain within the embankments and dam, and in terms of contaminants seeping, the quality of any seepage water. So any changes to the quality of the water in the groundwater underneath the tailings or in the seepage that's coming out underneath the embankments. In terms of for design of tailings facilities, then you need to do a hydrological, part of that will be a hydrological study where you'll need good information on precipitation and the hydrological nature of the catchment.
Yeah. Okay, I think this is the last question. I promise. Thanks for the great presentation. What is your perception of Chilean authorities about the use of these models? What do you think that Chilean authorities think about the use of these models? Do they know the models?
Well, we have had considerable interaction with CRHIAM as part of this project, and our impressions have been very good. You know, our impressions of being, you know, their people are really committed to improving the management of tailings storage facilities, including the old, small, and abandoned facilities, and that they're very interested in what we're doing, and that they're very open to suggestions about how things could be done differently in the future. I mean, clearly they are resource constrained. I mean, there's and they rely on research groups like ourselves to produce these new methods. I mean, I think it's very difficult for them to take initiative and say, okay, here's what research we need done, here's what tools we need developed, let's fund a research group to do this. It seems they can't do this, even though they're the ones who best know what needs to be done, right? So I think my impression of CRHIAM anyway is very good, and you know, we just need to keep working at that interaction and getting the best possible information from them about what they feel is the useful research. Yeah,
I think they actually do have a very good database. We were looking for information about the different operations all along the country, and there is a lot of information there in terms of the different types of minerals that each operation process, and even the tonnage, about the tonnage. So you can calculate so many things from those data for now and for the future.
Yeah.
So you can
the other thing that's, I mean, rather than focusing on mining, I mean, things are moving forward as well in terms of looking at water resources risks on a national scale. So there's been the CR2 project, and then there's been the climate risk atlas work. So all that stuff's quite impressive because it's bringing together a lot of relevant Chilean research groups to produce sort of national resources for doing risk assessments related to water. And at some point, so what we're trying to do is we're trying to take what that really good work, and we're trying to connect it with the mining context. So we're saying, you know, how can we use all these new developments more broadly on hydrology and climate? How can we use them to address some of the mining challenges? And I think there's more work to be done in making sure that these broader advances in the science are put to good use in the mining context.
Oh, yeah. Yeah, we are very interested also in connecting the mineralogy of the different operations with the water consumption and with the quality of water that you recycle from the tailings dam to the process, and to evaluate the impact of those, for example, those slimes that you recycle to the process, back to the process. So you are recirculating slime all the time.
Yeah.
That actually negatively impacts the production of the plant. Yeah. And then water recovery. So you kind of get into a negative cycle there.
Yeah, yeah. It's these you know, simple things with potentially large gains that, you know, that's the priority, isn't it, to pick up?
Yeah. Okay, Neil. I think we are going to end this CRHIAM International webinar. We are very grateful of your help, not only in this presentation, but in all the help you give us as a member of the International Scientific Council. We are very grateful of that, and we hope we can keep collaborating in the future in different areas.
Okay, well, it's been a great pleasure to do this and to contribute in this way. And the work you're doing in CRHIAM is really important and impressive. And you know, I just wish you all the best in
thank you,
in continuing that, and in continuing this great series of webinars that you're doing.
Very good. Thank you so much, Neil. See you soon.
Bye. Thanks everyone for calling in.
Thank you.